For the first part of this lab, we're going to combine lead 2 nitrate and potassium iodide using the method of continuous variations. So what I'm going to do is I'm going to put 1 drop of lead nitrate in the first well, 2 drops in the next well, 3 drops, 4 drops, all the way to having 11 drops of lead nitrate in the 11th cell. Starting with the first cell and using potassium iodide, I'm going to have 11 drops, then 10 drops, and then 9 drops, and then 8 drops, 7, all the way down to 1 in the 11th cell. And what that will do is it will alter the ratio in which I'm combining these 2 substances throughout the experiment. And so by looking at the results, I can make a determination as to what is the best ratio for combining these substances. And so I will start off with my lead nitrate. And then I will add my potassium iodide. So I'm starting with 11 drops in the first well this time. I'll give my plate a little shake, and then we will set this aside and let the reaction settle. Meanwhile, we'll do our next reaction. For the next reaction, I'm going to be using lead 2 nitrate with sodium oxalate. 1 drop in the first cell, 2 drops in the second, 3 in the third, so on and so forth. And the sodium oxalate, 11 drops in the first one. All right, give this a little swirl, and we will pull our other reaction into view and take a look at the results. So if I look closely at my results, I can make a determination as to which cell has the most precipitate. And in terms of the most precipitate produced, it's probably going to be cell 4, which was 4 drops of lead nitrate and 11, 10, 9, 8 drops of the potassium iodide. So 4 drops of lead 2 nitrate, and 8 drops of potassium iodide yielded the most precipitate. Looking at the reaction between lead 2 nitrate and sodium oxalate, I could see that the most precipitate looks to be, we're still letting them settle, but probably going to be cell 6 or cell 7. And so this is 1 drop of lead 2 nitrate, 2, 3, 4, 5, 6, 7. And then if it's 7 drops of lead 2 nitrate, then it's going to be 11, 10, 9, 8, 7, 6, 5. So this is a 7-5 ratio. That looks like what our result's going to be, but it might be this one as well, which is a 1, 2, 3, 4, 5, 6 to 11, 10, 9, 8, 7, 6, a 6-to-6 ratio. So because chemical equations typically balance with small number ratios, while our results looks to be about 7-to-5 yielded the most, I think if we let this one settle, we'll find that the 6-to-6 ratio or the 1-to-1 ratio is going to yield the most precipitate. And so we could record that as a result. A 6-to-6, 1-to-1 ratio is going to be the most effective. And so by continuously combining these 2 substances, in this case lead 2 nitrate and potassium iodide, and then lead 2 nitrate and sodium oxalate, I could determine what the coefficients would be if I were to take these substances and write them out into a balanced equation. Those would be the coefficients for the reactants. For the next part of this lab, we want to find the optimal ratio for when 2 different gases combust. To do this, I want to make a gas collection bulb. So I'm going to take a pipette and I'm going to cut off the stem. And the next thing I need to do is I need to calibrate my bulb. And so to do that, I need to fill this beaker up with water. And then I could take this bulb, submerge it, squeeze out all the air so it's completely filled with the water. And then I can determine the volume of the bulb by filling or by putting the water in the graduated cylinder. So I'm squeezing all the water into the graduated cylinder, and then I'm going to read the graduated cylinder, and it reads to be 4.9. So what I want to do is I want to take my volume of 4.9 and I want to divide it by 3. And when I do that, I get 1.6. So I'm going to dump that water out, and I'm going to refill the bulb. And this time, having trouble filling the bulb here. Okay, this time I want to squeeze out 1/3. And so 1.6 milliliters is what I need to squeeze out. And I'm gonna do that very carefully, filling it to the 1.6 mark. And I'm right there. And so now I could put a mark on this pipette right where the 1/3 mark is. And so I'm going to dump this out. I'm going to dry the outside of my pipette bulb so the marker actually can write on it. And then I'm going to take my marker and I'm going to mark the 1/3. So that is the 1/3 mark. I'm just going to squeeze out another 1/3. So I'm again going to the 1.6. It's not quite there. All right. And so I could set that aside. I'm going to dry the outside once more, and I'm going to mark it my other 1/3. So I have 2 marks on my pipette, splitting the bulb into 1/3s. I could then squeeze out the water. So now I can collect gases in here, hydrogen and oxygen. I could see the optimal ratio for combining the gases and causing the combustion reaction. So the next thing I want to do is I want to create 2 gas generators. One is going to create oxygen. So what I'm going to do is I'm going to take some yeast. So this is suspended yeast. So it's a yeast suspension. I'm going to take roughly 2 pipettefuls. Yeast is a fungus that decomposes hydrogen peroxide, producing water and oxygen. And so if I take some hydrogen peroxide and I add it to my test tube, filling it up most of the way, it will start reacting, giving me some oxygen. And so you could see that one's bubbling out, creating all kinds of oxygen. I'm going to take this other test tube and I'm going to add some pieces of zinc metal. That one doesn't fit. That one doesn't fit. None of these fit, of course. I need these smaller pieces, perhaps. All right, so I have some zinc. And next I have some hydrochloric acid. This is 3 molar hydrochloric acid. I'm going to take some and I'm going to add 2 or 3 pipettefuls, and I could see that it's already dissolving the metal and it's producing hydrogen gas in a very exothermic reaction. And so I could set that aside. I put my nozzle on the top, and there we go. We have our 2 gas generators. And so now I could take my calibrated bulb, fill it with water, and I'm going to test the combustion of these gases. First, I'm going to try just pure hydrogen. So 3 parts hydrogen, 0 parts oxygen. I'm going to, uh-oh, that popped right off. Make sure I get all hydrogen in there. I'm going to hold on to that. I'm going to hold my finger over it. I'm going to turn on my gas burner, and my valve is off on the bottom. So there I have my gas burner. Move my camera a little bit, turn my gas down. And I want to test the combustion of this hydrogen. So I'm going to squeeze the gas into the flame. I got a small pop noise. So I'm going to fill this back up. And this time I'm going to test the oxygen. So I'm going to put it on the oxygen. Let that fill up all the way. As soon as it pushes out all the water, I can grab it off of there. So I'm going to put my finger over it, and I'm going to squeeze it into the flame. Maybe a very small pop, if any at all. So we could say very small pop or none. And I fill it up with water again. This time I'm going to do a ratio of 2 parts oxygen, so 2 parts gas B, to 1 part gas A, so which is hydrogen. So get it to my 2/3 mark, and then get more gas A. There we go. Put my finger over that. I'm going to squeeze that into the flame, and I have a medium popping noise. Fill it up with water one last time to get my last ratio. This time I'm going to test 2 parts hydrogen, or 2 parts gas A, and 1 part gas B, which is oxygen. So it's filling up. I want 2 parts gas A to 1 part gas B. As soon as it fills up, pull it off. All right, and I'm going to test this one. And that one was a loud pop. It even extinguished my flame. So using the loudness of these combustions, we can make a determination as to the best way to combine these 2 gases and create a combustion reaction. So hydrogen and oxygen, what is the best ratio between them? So based on the loudest pop.